Hey guys, my name is Shashank Kalanthi, and today we're doing a video on practical statistics for data scientists, chapter 3. Chapter 3 is about significance testing, I believe, and it is a bit of a long chapter. That's why this video took so long to come out. And I have more videos. If you're new to the channel, we have videos on chapter 1 and chapter 2 on the channel, and we also have a live stream every Thursday and Friday where I answer whatever questions you might have about being a data analyst. And I'm actually on my journey to become a data scientist. So I can answer some questions about being a data scientist as well. I also have an overview of the book Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. And just some other videos. I have a 3-hour Python tutorial, like an hour-long SQL tutorial, like a 3-hour-long Tableau tutorial, where basically I'm trying to create as much content as I can to help you guys enter the world of analytics and data analysis. So if you're at all interested, feel free to subscribe. And if you're really interested and you would like the notes for this video and for all of my other videos, be sure to either join the YouTube membership or to join my Patreon. It's a great way to support the work that I do and make sure that this is still a like a profitable enterprise for myself as well. I try to make as much useful content as I can for you guys, and recently I've actually revamped the Discord with a bunch of new channels and everything. I got this like developer who was able to like create all of this for me. And what I'm trying to do with this Discord is I'm trying to create a community where we are able to help each other out, and we have systems in place to make sure that we're studying a little bit every single day, and we're tracking our progress, and we're progressing regularly. And so I'm trying to build out some kind of like tools and bots inside Discord that help us all do that. So without further ado, I think that's about it for my intro. Let's go ahead and get started. Oh, one other thing. I also do want to bring some attention to the practical statistics for data scientists. The guys that made this book have a GitHub with some code inside it. This isn't as good as the hands-on machine learning book's code on their GitHub, mostly because hands-on machine learning, like everything, to do anything there, you had to do it in Python. I mean, you had to do it in code. But this book has a lot of like statistical concepts that like code just isn't really written out for. So that's just some information I wanted to share with you guys. So let's go ahead and close these tabs and let's get started. So as you can see over here, we have something like almost 4,000 words in the notes over here. And as we go through this chapter, I'll probably be adding a couple of things here and there, but this chapter was a doozy. Statistical experiments and significance testing. Let's see what we got over here. Let's see, I have a message. Okay, cool, that's important. All right, so one thing I also want to note is be careful with the Python code in this chapter of the book. I should probably say that. Some of it doesn't take advantage of Panda's better functions and doesn't work outside of the like specific examples that they give. So, for example, their resampling code, I wrote a version of it which I believe to be better and to use some of Panda's methods a little bit better than the one that they wrote, and would work in more disparate situations. So, just a heads up for you guys. All right, let's start off with A/B testing. So, A/B testing is a common tool used to compare two treatments against some group that you're testing against. An interesting example is headlines on news articles. Websites will test headlines against one another by showing different headlines to readers of the same article to see which one actually performs better. There's a great New York Times article I link over here where the New York Times actually talks about how they do this, and they use it to make sure that headlines are catchy enough for where people will actually read their articles, which makes a lot of sense. I mean, I'm sure you've all been in a situation where you're talking to someone, they're like, oh, I read this article, and you're like, wait, did you read the article or did you read the headline? Just goes to show how important headlines really are. And if you're trying to test up our, let's see, we need to measure the efficacy between groups A and B, right? And we usually do that using something called a test statistic, which, excuse me, can be binary in the case of the headline example we just covered, or if we have a continuous variable like revenue, it can be something like using the means of the two classes and comparing those two. So, and I have a little caption over here of the interesting part where it says, the Times also makes a practice of running what are called A/B tests on digital headlines that appear on its homepage. Half of the readers will see one headline and the other half will see an alternative headline for about half an hour. At the end of the test, the Times will use the headline that attracted more readers. And people think if you change a headline, that's some kind of gotcha. And it's not, says Mark Bulick, senior editor who oversees digital headlines. People who think it's a gotcha just don't have a full understanding of news in the digital world. And I see what they mean. At the end of the day, if both headlines are accurate and both are like informative headlines, then I don't see anything wrong with testing which one is more interesting to viewers, you know. But that's where kind of like trust in the organization is quite important. And, you know, you got to determine, okay, which news organizations do I decide to trust. So If you're trying to test something, if something is effective independently, such as a drug versus not using a drug for treatment, it's important that you not just test how effective the treatment is, but you have to have a control group of some kind, which allows you to test the efficacy of the treatment against a group that represents the norm. So this is kind of what this would be in, like, the world of, I was about to say the drug trade, but in the world of drug testing, is you would have a placebo group where you feed them like a sugar pill or something. Basically, they don't know whether it's real or not. And usually the tester doesn't either. It's supposed to be double blind. That way they don't treat you any differently. And you give another group the actual drug to see, okay, is this drug actually performing better than the norm? And the reason that this is important is because in the real world, there are actual consequences for change. And you probably don't want to change things unless you have some reason to believe that change is actually beneficial. In the context of drugs, it's probably better to go with whatever treatment or whatever, like doing nothing or using whatever is already existing and has potentially been there for years or decades, rather than a new drug if the new drug doesn't show significant improvement in the quality of health of an individual. Or in the context of, say, a website, if you're testing your current website versus a new website, changing a website can be an entire process, and you don't want to go through that process if the new website's not even better than the old one at, say, converting people from free subscribers to paid subscribers on your website. So that's why A/B testing is important, and that's why hypothesis testing, which we'll go over in a second, and significance testing is very important. So A/B tests are relatively simple, and while useful to data scientists, they're only one part of the toolbox that includes much more interesting multi-arm banded testing, which I'll show you at the end of the chapter. There's a great article on Towards Data Science on A/B testing that I read, and I linked a Kaggle workbook over here. Here's the URL for it, on a full A/B test implemented from end to end by this guy, Matthew Zhang. And the reason that I didn't write out a bunch of code for this is you can see, how long this is. And this is just for an A/B test. So I'll probably have an entirely separate video where I perform an A/B test on some data, because, an A/B testing is just one part of this entire chapter. We have a lot more content to go over. So hypothesis tests, also called significance tests, are designed to help us manage the human tendency to incorrectly understand, interpret, and predict natural random behavior. And it does this by testing change due to a phenomenon compared to a baseline of some kind. A great example of humans being really bad at predicting randomness is if you tell a human being to write out 1,000 heads and tails, like on a piece of paper, to simulate a random coin flip, they actually will almost never write like 10 heads in a row or 10 tails in a row, which is actually very likely to happen if you flip a coin 5,000 or 1,000 times, because that doesn't seem random to us. For us, random seems like constant change. Like constant change is what most humans associate with randomness, when, like little bouts of consistency are going to happen in a random distribution. So that is what hypothesis or significance testing is supposed to help us out with. Let's go ahead and add that in there. So we need something called a null hypothesis and an alternative hypothesis. The null hypothesis generally says that a treatment will cause no difference that can't be attributed to random chance, and the alternative hypothesis says that the difference caused by the treatment is significant. We generally want to prove the null hypothesis wrong. So what we do is we do something called a two-tailed test or a one-tailed test, which I'll go over in a second. And basically what we want to do is we'll have a null hypothesis. So let's say we have a website, right? Or let's say we have those drugs, for example, right? And we have a new drug and we want to test it against doing nothing for some disease of some kind. The null hypothesis would be that drug A causes no significant improvement in the health of a patient in relation to disease X or whatever. And the alternative hypothesis would be drug A does cause a significant difference or significant improvement in the health of a user whenever they use this drug. So that's the null and the alternative hypothesis, and we want to prove the null hypothesis wrong, basically meaning that there is a significant difference between doing nothing and giving someone the drug. One more consideration is to whether we should run a one-tailed or a two-tailed hypothesis test. If you look at the image below from statisticshowto.com, then you'll see that the two-tailed rejection region, and it's called the rejection region because that's where we reject the null hypothesis, the rejection region's on either side of this distribution over here, and with a one-tailed test, it would only be on one side, meaning that we only want to see results that are better than something, for example. And we have something called an alpha value, which is basically the size of these regions over here. So the alpha value is usually set to 5% or 1% of the distribution. And what that would mean is if it was a 5% alpha value on a two-tailed test over here, in either direction, it would be the top 2.5% or the bottom 2.5%. So let's see. I don't think I wrote alpha value over here. The size of the yellow region is determined by something called the alpha value. And we'll be going over that a little bit later. All right, next they go over something called resampling. And you'll see in this chapter, I'm actually cutting down a lot of the material because this chapter is like very long. And let me take a break over here and actually explain like what is the purpose of this video specifically. I believe this video, I hope, is an addendum to you already reading the chapter. I kind of just want to go over it and see if I can help digest the material a little bit more. And what I've learned is that you know, in my time, like learning a bunch of content without ever applying it is not very useful. So what I want to do is I want to provide a high level overview of what's going on in this chapter. And then as you need to use something, you'll be like, oh wait, I know what A/B testing is at a high level. I could probably use that. Let me go ahead and, you know, pull up these notes and click on this Kaggle over here to go ahead and test out what the actual A/B testing is. Or to actually see what A/B testing is. And then like you'll learn it from there. That way you can implement it immediately and actually learn it. So that's kind of what we were going for with these notes, just to clarify that. All right, so resampling, this is where we're gonna be writing some code. So resampling is the process of repeatedly taking sample values from observed data to assess the variability in a statistic. And there are two basic types of resampling. There's bootstrapping and permutation tests. So let's go ahead and highlight that. I believe we went over this in chapter 2 as well. So bootstrapping tests the reliability of an estimate. Values are selected with replacement, meaning that you can select the same instance of a variable more than once. So for example, you know, if I have like these 3 items on my desk over here, you know, I have a sticker and then I have 20 rupees over here, the Indian currency, right? If I was sampling these pieces of paper over here, then I could sample one, and then bootstrapping is I replace it again, and then I sample again, and then this time I pick the sticker, but if I do it again, then I can pick the exact same bill all over again. So that is bootstrapping. A permutation test, on the other hand, you'll mix groups together and draw samples with sizes equivalent to the original group sizes, and then collect your sample statistics from them, and the process is actually outlined below. Oh, and then sorry, I should probably write resampling with replacement. Same as bootstrapping, except you replace the contents of, or you replace your selections. Yeah, there we go. And then we have something called the permutation test. Something I enter over here so there's a clear division. And it's used to test hypotheses. What happens is you'll mix together groups and draw samples with sizes equivalent to the original group sizes, and then collect sample statistics on them in the process outlined below. So let me go over the process, and then we'll actually like implement it with some data. So what happens is you'll have group A, group B, and group C. So yeah, and we'll go over what this is in a second. You take all of the groups and then you combine them into one group. So you'll have the permutation group over here. And then you resample groups of the same size as the original groups and repeat that R times. So for example, you'll take that permutation group, right? And remember, group A was 12 values big, group B was 8 values big, and group C was 4 values big. And then you just resample, usually in a bootstrap method, until you create groups of the same size, and then you collect sample statistics on that. So for example, you'll take the mean of this, or the percentage of, I don't know, green or like red values or something like that. And then after repeating the permutation process a few times and creating a constituent histogram of your statistics, then compare the original statistics with the distribution of statistics produced by the original permutation method. If they are significantly different, then you have proved that there's a significant difference between 2 or more groups. The process outlined below is called the random permutation test. We can perform something called the exact/exhaustive permutation test, which will create permutations of every single combination. And this is only possible with small samples, as the complexity of running such a test grows exponentially with each new sample. So we have some code over here, which I believe is a more general purpose version of the permutation function in the book that we can go ahead and use. So let's go ahead and copy this. And then let's go ahead and open Visual Studio Code. You know what, let's just open up the chapter area of open. All right, cover this up to limit distractions. All right, so I should be able to run both this. Oh, whoops. I need to run this on this. So we imported all of those libraries. Then I went ahead and created my permutation function. And then what I need to do, let me go to where I actually run it. I believe, yeah, I have this data over here. This is data from that Kaggle workbook we opened up a little bit earlier. And yeah, there's a data cleaning procedure that is in the same Kaggle notebook. Oh, do I not have it in? I don't have it with me right now. Let me go ahead and download the data. Okay, cool. So then I should be able to go back over here and run this code again. All right, and you'll see we have user ID, timestamp, group, landing page, and converted. And then what we do is we do some of the data cleaning stuff that they, these were just like some scripts that were inside that notebook, so I just copied them because I don't have to actually understand this data. And then I believe in order to actually run the resampling procedure, I do, let me copy what I have over here. There we go. And I'll explain what this code does in a second. So what this function I created does is you have three inputs. You have a data frame, a data column, a grouping column, iterations, and a statistic function. And basically what this is the data frame is just, whatever data you want to look at. The data column is the actual numerical column you'll be running your statistics on. So in the case of this data over here, that would be converted, because a 1 means converted, a 0 means not converted. And then you have a grouping column, which is this group over here. So for example, we have a control page and a treatment page, and or a control group and a treatment group, and I want to know the conversion rate over there. What I actually need to do is I need to create a group landing page together column, but that's not really necessary for what we're doing right now. Iterations, how many times do you want to resample this data? I picked 100 because 1,000 actually takes a little bit of time to do. And then a statistic function. I picked np.mean, numpy.mean. And you'll see over here, we actually created a data table that has the mean of the treatment and the mean of the control. And we can go ahead and create a histogram with this data. So I think I can just do, let's see. We'll call it new or permutation data equals this. Let's go ahead and run that. And then we'll do permutation data. And I believe, yeah, it's called treatment. I think I just do .hist. There we go. And we'll see this is the histogram of the means of the permutation data. And then let's see if we can do permutation data control.hist. Cool, and actually it overlaid them, which is awesome. I wonder, is there a... okay, there's not an alpha variable. So alpha is usually in the context of graphics, alpha is the variable you use to reduce transparency or increase transparency. But as you can see, this data looks almost exactly the same. And really, the way I should have done it is I should have grouped the group and the landing page together, and not just the group itself. And actually, you know what? Let's go ahead and do it that way. So let's go ahead and create a new column. And we'll see, we'll call it in the df2 data frame. And we'll call it group landing page. And then we'll just say it's group plus landing page. Then I need to do df2 and then surround this with brackets. So I'm literally just concatenating these two columns together. And if you're wondering anything, if you have any questions about what I'm doing, like from a Python syntax perspective, feel free to check out my Python tutorial. It goes over all of this content as far as like the actual like Python aspect of it. So you'll see group landing page is a new column. So let's go ahead and change that to that. Oh, and then this won't work anymore. Yeah, this will error out. Okay, so. Oh, interesting. Oh, so all the treatments are new pages and all the controls are old pages. Okay, no, so never mind. It was accurate before. So in that case, let me do 500 tests and see if that comes up with a different number. It might take a second to run. But that's the basics of how you run a resampling method. And then this code over here, which you can dissect, will show you, will actually run a resample for you on any data that you end up giving it. So if you're interested, they are available right over here. And next we'll be going over statistical significance and p-values. So it's going to take a second to run. Ah, there we go. Yeah, and you'll see the data is becoming more and more normal. And it looks like, let's see, blue is treatment. The treatment is slightly to the left of the control, but really can't be for sure. Let's go ahead and run 5,000 and see what happens. So we'll go ahead and run that, and then we'll just have that running in the background, and then we'll just come back to it later, because that'll take a second to run. So, statistical significance and p-values. Results greater than the realm of chance variation are considered statistically significant. P-values help us more accurately use the permutation testing method to determine if a result is within the realm of random chance or it's significant. If it's significant. The p-value represents the proportion of times that the chance model, a permutation test, right? So the chance model produces better results, that produces results more extreme than the observed results. So what does this actually mean? So if you remember, every time we ran that test, there was a new row in, every time I did a permutation, right, there was a new row in our data. And that is basically what we're trying to test. We're trying to see if the proportion of times that the chance model, each of those rows that I just showed you from the permutation test, produces results more extreme than the observed result. And this value can be estimated by taking the proportion of times the permutation test produced a result greater than or equal to the observed difference. Now that we have the p-value, how do we know what is considered an extreme value? We usually set some threshold the p-value needs to be greater than prior to our testing. By convention, this is usually 1% or 5% and called the alpha. Because it's often misunderstood, p-values are misunderstood quite a bit, I'm going to copy the book's definition of p-values here. It's the probability that, given a chance model, results as extreme as the observed results could occur. And p-values, one interesting thing is the American Statistical Association released a p-value statement fairly recently, where it was becoming such a problem in academic research of people using p-values incorrectly that the ASA actually released a paper explaining like how they should be used and how they see the accurate usage of p-values being. So I'll go ahead and link that in the notes available over here. Create bookmark, and then we'll say the usage of p-values in academic literature is so fraught with misuse. Shorten that. Are so fraught with misuse that the American Statistical Society, I think that's what it's called. Wait, is it? No, that wouldn't make any sense. Association, that was it. Release the above guidance on properly using them. There we go. So let's put that little note over there. I'm curious if we end up at 4,000 words by the time these notes are done. We might. We're at 3872. So in reference to that, there are also things called type 1 and type 2 errors. Type 1 error is concluding an effect is real when it's really just due to chance, so it's a false positive. And a type 2 error is concluding an effect is not real when it is real. So type 1 error would be something like you think a drug was effective when it actually wasn't. And a type 2 error is thinking a drug is not effective when it actually is, based on your testing. And significance testing is designed to protect against type 1 errors, where we basically think a effect is real when it's just due to chance. And, if you remember what we just went over, that makes perfect sense. And for data scientists, p-values serve as one piece of information in determining if the result of a model is interesting or not. It shouldn't control the results of your work, but be one component of it in comparison to academia, where it's scrutinized more thoroughly. And this chapter is really where we start getting into kind of the difference between traditional statistics and data science in its importance. Data science, at least in the corporate world, is very focused on getting concrete results for the company. And academia is very much focused on discovering new knowledge, which requires you to be a lot more rigorous in the process by which you actually go about your analysis, versus in data science, it's kind of like, if what I did worked, that's really what matters at the end of the day, You should be able to explain it, but, it working is probably the most important thing. Okay, so my fan's turned down, so I'm guessing that the test was done running. Cool. Took about 5 minutes. Yep, and you'll see, if you remember from the previous chapter, the more and more tests you run, the narrower and narrower your distribution tends to get. So you'll see this is actually a lot narrower than what we had before. Why not? Let's just run it. Well, no, I can't run it 50,000 times. That'll take 50 minutes to run. So let's go ahead and run it 20,000 times. Curious to see if this does anything interesting. So I knew that the test stopped. I knew the permutation test stopped running because the fans on my computer, stopped spinning as much. So the t-test is, let's see, there we go. The t-test was named. The t-test was named after the student's t-distribution, which was covered in the last chapter, and it was used in a time before researchers and statisticians could run thousands of permutations necessary for the permutation test, kind of like what I'm doing right now. Like, if you think about it, right, prior to computers, how would you run a test 20,000 times, Whereas, now it's really easy for me to run it. And if I had a more powerful computer, I could probably run this 200,000 times. Or honestly, if I had more time, there's a reason I couldn't run this for 8 hours straight. So, I'm able to run it 2 or 4 million times, So the t-test is used to determine if there's a significant difference between the means of two groups, and it can be implemented quite easily. So here is the code, and let's go ahead and see if we can implement it. So I might have to open up a new workbook because this one is still running. So we'll just call this new workbook.ipy notebook. And then let's go ahead and put this in here. And then we'll go ahead and get our libraries again. Minimal data science. And if you're wondering what minimal DS stands for, what environment that is, I have that in one of my first videos where I actually talk about how I set up my data science setup for productivity. So go down to one of my first videos and if you type in productivity, then that's where you'll find the video. So it says stats is not defined. Okay, so scipy.stats, I called it SS. So we'll go ahead. Okay, cool. And then obviously because I haven't actually defined any data, then nothing's gonna pop up right now. So what I need to do is I need to go over here and I need to import this data that we have. Along with the data cleaning procedure. So this is straight from the book. I'm going to modify it for our data. Where are we at? There we go. Need to clean this up. All right. And then I need to basically replace this session times with df2. And I want group to be lowercase to equal, and let me write that the way I normally write it. I don't use dot, or I don't know if you call it dot notation, but I don't use the dot method for accessing columns, just because columns oftentimes have spaces inside them, which the dot method doesn't work as cleanly. So group equals control. And then the actual like column I want to access to measure on is going to be converted. And then this needs to say treatment. And then we want to use that same converted column, so let me just copy this over here. P-value for a single-sided test, NaN, interesting. What happens if I turn this to be true? Oh, you know what? It might have to do with the... It might honestly have to do with the distribution of the data. I wonder what happens if I do dot mean over here. Oh, whoops. Need to actually run the method. Huh, weird. So let's see what value this gets us. Oh, this is supposed to be control. No, so it doesn't do anything for us, so let's see what we can get here. And then if I drop the mean, so maybe, there we go. Okay, so it's because I misspelled control. So you see the p-value for a single-sided test is 0.0948. Let's go ahead and copy this, go back over here, and we'll paste our new code. And the code outputs a p-value, which we can then compare against our original expected p-value to determine if we can reject or fail to reject the null hypothesis. So if you remember, it needs to be more, so this is 0.09, which is, and let's say our original value was 0.05. All right, so given that our p-value is 0.09, what we're looking for is we're looking for a p-value of less than 0.05, which was our, remember we were, 5% was kind of our, was our alpha. So it looks like there isn't, we don't have enough information to reject the null hypothesis in this instance. So let me go ahead and add this in there. Running the code, we get a p-value of, whoops, which is greater than our .05. We need to reject the null hypothesis. So we fail to reject the null hypothesis given this data. And let me go ahead and add a little bit more of an explanation over here. So we first need to determine a, oh, let me go ahead and add that import as well, just so that's easier for you guys to follow this. So we first need to determine what alpha value we're looking for, and then calculate our p value. Let's settle on an alpha of 0.05. There we go. That way the explanation's a bit more robust. And this code outputs a p-value, which can compare expected alpha, or compared to our alpha. There we go. To determine if we reject or fail to reject, which is greater than 0.05. In order for the p-value to be more extreme than our alpha value, it to be lower than it. There we go. Cool. So that gives a little bit more meat to the bones that we have written out over here. Okay, cool. We're at 39.56. I think we'll hit 4,000 if we try a little bit. So that's your t-test. Investopedia actually has a lot of tremendous articles on this stuff, and here is one over here on the t-test that I highly recommend reading. So I'm guessing it has to do with like quantitative finance is why they have all these articles. So that's I recommend their stuff. Here's if this is still running. Yep, still running. 20,000, right? So it should probably take 20 minutes. Yeah, I think it's about 1,000. I mean, a minute per 1,000. All right, so let's go back to our notes. Next, we're going to be going over something called multiple testing. So with the explosion of available data in the world over the past couple of years, the quote at the beginning of these notes is true now more than ever. And that quote was, if you torture data long enough, it will confess anything. Let me italicize that. Statistically speaking, if you try hard enough with a large enough data set, you will find statistically significant correlations even if none actually exist. And if you have a particularly complicated procedure that you want to test, such as a clinical trial, for example, where you might be testing results of a therapy at multiple stages, you increase your chance of classifying a chance event as statistically significant. And this can be compensated by using these statistical adjustments that make the bar for statistical significance more stringent. So if you want to go check it out, check out Bonferroni's adjustment and Tukey's HSD. The book doesn't go into any detail about them, so I won't over here either. Next, we have something called the false discovery rate, which across multiple tests is the rate of making a type 1 error. Alpha inflation is the multiple testing phenomenon in which the probability of making a type 1 error increases as you conduct more tests. And then adjustment of p-values accounting for doing multiple tests with the same data. So that's kind of like what we see with the Bonferroni's adjustment and Tukey's HSD. So the book doesn't go into too much detail about this stuff. There are multiple ways to handle errors that occur with multiple testing, and the methods used by statisticians will differ from the methods used by data scientists. So data scientists, if you were watching my hands-on machine learning tutorial, then you'll see how we ended up dealing with a lot of these problems. These problems basically end up, one way they end up getting you is through overfitting. And so when using typical data science methods, you'll mitigate some of this risk through cross-validation, which will test your algorithm on multiple cuts of the same data, and a holdout set, which the algorithm is not trained on and instead is tested on after the fact to ensure you're not overfitting your data. So basically, in the world of data science, where we typically end up having like a lot of data to work with, a common thing to do is to have something called a holdout set, which is you take your data and you split out maybe 20% of it, right? And you train your data, you create a machine learning, or you train your machine learning algorithm on the 80% of data, and then you evaluate its true efficacy on that 20%. That way, if it finds a correlation that doesn't actually exist, or it thinks something is significant which isn't actually significant, then it won't necessarily affect your final results, because you'll know, because if that's the case, it shouldn't work on the holdout data set that you have. So that is one of the many ways we handle it in the world of data science. Next, we go over degrees of freedom. And the degrees of freedom of a data set is calculated by taking the number of values n and subtracting 1 from it. The logic being that if you have 10 values and you know 9 of them, the mean, if say you want to calculate the mean, right? Let me rephrase that. The logic being that if you have 10 values and know 9 of them plus the mean, the 10th value can only be one number. The Investopedia article over here has a great alternative explanation of the concept right over here. So just Investopedia terms, degrees of freedom. And we use n-1 in our calculations of simple variance and standard deviation, if you remember from, I think, the first chapter. And this is because when taking a sample, our variance or standard deviation will be biased slightly downwards if we use n in the denominator. So we free ourselves of that bias by using n-1. When working with sufficiently large data sets, obviously a n-1 versus n will make no difference to what we actually do. So it doesn't really matter if you use a sufficiently large data set. And degrees of freedom also helps explain the dummy variable trap. And this is a situation in which you are taking a categorical variable like the days of the week and encoding it to a numerical variable. And you normally do this through something called one-hot encoding, which basically is the process of making n-1 binary variables that represent each day of the week except one, assuming you're using days of the week. Let's see. Each category. Except one. And the reason we use n-1 is because if we get a 0 value, so the reason we use 0 is because if we get a 0 value for all of our other dummy variables, we automatically know what the... Oh, shoot, no, I actually had a good explanation over here. So I'll leave it as is. There we go. The explanation is if you're like one-hot encoding like the days of the week, so if that's like a single column, then what happens is you create a new column called Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and you have a 0 or a 1 depending on if that row of data was a Sunday or a Monday or a Tuesday. And the thing is, you need to actually remove the Saturday or one of the variables, because if 6 of the days of the week are encoded at a 0, meaning that it's not any of those, then you already know it's the last one, and you need to make sure you avoid a problem with multicollinearity. So you'll see I have an illustration over here which you can expand by clicking on full screen. And you have a numeric, let's see if I can expand this a little bit. Okay, cool. You'll see I have a numerical variable, and a categorical variable. And what I did is when I one-hot encoded it, I took the categorical variable and I turned it into 3 different columns, because we have Toyota, Honda, and GM. Those are the 3 different variables we have here. And on row 1, the value is Toyota, so that cat var Toyota is 1, and cat var Honda and cat var GM are both 0. And you do that for every other row. And then you go ahead and you remove one of the columns, cat var GM, because I already know if, for example, this is cat var Toyota 0 and cat var Honda 0, then I automatically know that cat var GM is going to be 1. And we want to avoid a multicollinearity situation where multiple values, that multiple columns are perfectly related to each other, because that can really mess up your predictions. That can mess up your machine learning algorithms. So that is degrees of freedom. And you'll notice in this chapter, some of the concepts don't seem to really tie together. That's kind of the way I felt about this chapter, but yeah, that's just kind of the way it was designed. Next, we get into ANOVA testing. And ANOVA testing, so we have a pairwise comparison, which is a comparison between a summary statistic of different groups. Omnibus tests are single hypothesis tests of the overall variance among multiple group means. And the decomposition of the variance, separation of components contributing to an individual value, and an F statistic is a standardized statistic that measures the extent to which differences among group means exceed what might be expected in a chance model. So this will make sense in a second. So the ANOVA test tells us, or helps us compare multiple groups of treatments, or treatments against one another all at once. So when we're using the t-test can only compare 2 means from 2 different groups with each other one after another, whereas an ANOVA test can compare multiple variables against each other at the same time. And I think I'll put analysis of variance. Okay, so my computer fan should stop spinning, so let's go ahead and see if this finished running. Looks like it did. We have 20,000 runs. Yeah, and it looks about the same, I guess. So that's basically our distribution right there. So they're basically the same thing, it looks like, which jives with our t-test that we ran over here, where our t-test was saying that, there's not a significant difference. Then let me go ahead and put this over here. Oh, okay, and then one question you might ask is, let's say you have 4 website designs, right? And you want to check which one is better than the other ones. Why can't we just do a pairwise test against of every site against one another? And this goes back to the multiple testing section of the chapter, where if you test enough groups against one another, like one after another, then you might run into a correlation or think something is significant when it actually, or think significant something that actually isn't significant. There we go. And ANOVA test helps us test for statistically significant differences between groups, basically. And here's a procedure for actually executing on an ANOVA test. So first, combine all the data from all the groups together, shuffle and draw resamples from each group of the same size, record the mean of each group, and record the variance amongst the means of the groups. Repeat steps 2 through 4 many times. And the proportions of resample variance that need to be observed, the proportion of resamples variances, so it needs an apostrophe, that exceed the observed variance is the p-value. So, let's see. Let's go ahead and try and run this on our data. So I'm going to go ahead and copy this. And let's go run this on our data. So we'll paste this over here. Oh, but we can't run it on this data because I'm going to need at least 4 groups. Like I can't do an ANOVA test between 2 groups. Okay, so we'll leave this code as is in that case. So what we're doing over here is we're taking some, we're grouping things by pages, taking the mean and then the variance of the means. Oh, you know what? Actually, I have this data. Yeah, I think it's the click rates data. Is it the click rates data? Yeah, I think it's the click rate data. So let's go ahead and import that. Oh, no, it's not. So let's go ahead and download the data from their GitHub. There it is. Click on the raw and then save as. All right. So let's go ahead and import our data. So pd.read CSV. There we go. And then let's go ahead and run that. Okay, cool. So we got the means for each of the pages. It looks like there's a page 1, 2, 3, and 4. And I'm guessing these times stand for load times or something like that. Variance of 55, okay. And then if I run this, oh yeah, it's gonna be like some formatting error or something. Oh, there's our issue. Okay, so the p-value is this over here. So again, if we take the same example of using 0.05 as our alpha, then this doesn't make much sense, or this p-value isn't particularly good, and we don't necessarily know if anything has changed, or if there's a significant difference between the pages. The only thing I did was I pressed enter over here. There we go. And like we have t-testing for the permutation testing, we have the Fstatistic for ANOVA testing. The Fstatistic is one of the outputs of an ANOVA test, and the t-statistic tells us if, where the t-statistic tells us if a single variable is significant. The t-statistic tells us if there is a significant difference between a statistic of two groups. Oh, whoops. There we go. Well, the F statistic tells us if a group of variables are significant together. And the below code outputs what's called an ANOVA table, which has a lot of useful information about the ANOVA test. So let's go ahead and copy this. And then we can go ahead and run this over here. For sesh is not defined. So for sessions. Stats is not defined, so I call that SS. There we go. So we have our p-value, and running the test this way, it looks like we actually have a significant p-value, meaning that there is actually a significant difference between these values over here. Here is our F statistic. Mean squared of the residuals, over here. The sum of the squares. And then DF, I'm guessing this is the number of records we have, correct? 16, no, that doesn't sound right. Oh, sorry, our F statistic is over here. So we're doing a one-way F test over here. So let's go ahead and copy this code. And then paste this over here. And you'll see this weird notation over here. My understanding is this comes from R. I didn't really understand it, but that's just kind of the way stuff is noted. So let's go ahead and reduce that over there. And we're at 3980, so I'd say 20 more words in order to reach 4,000. And that is the ANOVA test. So basically you use it to test if there's a significant difference between, in the variation, or a significant difference between multiple, like a group of multiple items. So not just two different groups, but multiple groups. And then finally, as far as the testing is concerned, we go over chi-squared testing. And while ANOVA testing determines if the means between two variables are significantly different, chi-squared testing determines if the data fits an expected distribution. So let's take our web page example for again. The null hypothesis would be something along the lines of there is no difference in the click-through rates between websites A, B, and C. And assuming this is true, we would test all three websites on 1,000 users apiece and measure the click-through counts. Let's say we get 10 clicks for site A, 50 for site B, and 80 for site C. And this makes sense. Click-through rates are actually very, very small in any kind of internet marketing. The chance of someone actually clicking on your ad are very, very tiny. And let's say we get 10 clicks for site A, 50 for site B, and 80 for site C. Assuming that our null hypothesis is true, we expect that the expected click-through count for each website will be 10 plus 50 plus 80 divided by 3, or 46.7. We can then calculate the Pearson residual through the formula, observed minus expected over the square root of the expected. And then the chi-squared statistic is just a sum of all squared residuals. This is considered our observed chi-squared statistic. And we can resample to compare to the proportion of sum of square deviations that exceed the observed to get our p-value. So just to recap, remember this is what residuals are. I got this from the statisticshowto.com website. Basically, it's the difference between our expected and our observed values. And we can use the SciPy package to calculate the p-value using the chi-squared distribution as reference. So if I copy this over here, I think we have a slightly different data set we use for this. So these change to SS, and then clicks was a data set that, this is a separate data set, so this was, whoops, not here. Let me go ahead and open up the clicks. This is also in that GitHub. It's down here, actually. There we go. This is just some sample code that they ran. I'll go ahead and put this inside that as well. And you know what? Let's go ahead and just throw in the CSVs over here. That way, it's easy for anyone that just runs across these notes to pull the data as necessary. And then I think AB data was the one I used over here. So import, or sorry, we say df2. So let me actually go ahead and insert that little cleaning thing we did with df2. There we go. And I'll go ahead and format this a little bit later to make it cleaner. I wonder if that counts as words, actually. Nice, we're at 4024. Code counts as words in this. That's awesome. I didn't actually run this code, did I? So let's go down to the bottom over here. Let's run this and then that. Chi2 squared is, Chi2 observed is not defined. Oh yes, there's a little bit of extra, there's a little bit of an extra code that I need to add over here. So let me go ahead and add that in. So this is from the book. Let's see if this is enough. Chi2 observed is still not defined. Oh, did I not? I thought I... Oh, I got rid of it. Okay. Sorry, there was a lot more code over here and I just got rid of a bunch of it. And it's so hard to copy. Like, the code in this book is formatted so weirdly. So let's go ahead and put this in here. Hopefully. There we go. So observe chi and then our p-value, so we can go ahead and add that in there. And make sure we import our data as well. And then finally, let me go ahead and make sure my import statements are in here. I need pandas and SciPy stats. All right, there we go. And that's how we run a chi-squared test. Now there's something called a Fisher test too, which is basically a more exact version of the chi-squared test. It's called the Fisher's exact test. The problem with it is that it gets computationally more and more intensive the more variables that you have, and there aren't any common libraries to perform the Fisher test on if you have more than 2 variables, basically, in Python. In R you can, but in Python there's nothing there for it. But you can use the scipy.stats.fisher exact method for 2x2 tables called contingency tables. And then classically, Fisher and chi-square tests were used to see if an effect is real or more likely a product of chance. In data science, we typically use the Fisher and chi-square test to better determine if a feature or column in a data set has significant enough effect to warrant further consideration. Now getting to the exciting part of a multi-arm bandit algorithms. So although it sounds super complicated, a multi-arm bandit algorithm is just supposed to allow us to pick the most effective treatment from a number of treatments while testing other treatments in order to allow for more information to better train our algorithm. In short, if you have treatments A, B, and C, let's say they're from different headlines for a news article, and we know that A is more effective than B, which is more effective than C, instead of just showing people A, kind of like the way the New York Times does, right? We show them A at a higher rate than B, and show B at a higher rate than C, in order to use the best headline while continuing to collect information in case conditions change, or we didn't collect enough information to make any judgments early on. I can imagine the reason that the New York Times does this is because it would probably seem quite off if people were consistently getting different headlines with between each other, and that's probably why they just kind of settle on the headline and they're like, okay, this is the one we're going to be using. There's a great explanation of this on the Analytics blog, reinforcement learning guide, solving the multi-arm bandit problem from scratch in Python. So this is a great guide to use in case you're interested. And then finally, we go over, we go over something called power and sample size. And power refers to the probability of detecting a given effect size with a given sample size. An effect size is the minimum size of the effect that we hope to be able to detect in a statistical test. Basically, how much a treatment needs to improve outcomes for us to institute the new treatment. Power is usually used to determine sample sizes if we want to decide between 2 ads and we want to pick ad B only if it's 10% or only if there is a 10% or greater improvement in it over whatever we're currently using. We need to determine what sample size will produce the results that are significant enough for us to determine this. There are 4 moving parts we need to coordinate. We need to coordinate the sample size, the effect size we want to detect, also called the minimum desired effect, the significance level, or alpha, and our power. If we have 3, then we can calculate the 4th. So for example, in this code over here, if you have the sample size, the effect size, and the significance level, then you can calculate the sample. If you have the power, the significance level, and the effect size, you can calculate the sample size. Another way to calculate sample size is to use something called, to determine what sample size you should use is by using something called a power curve, which there's a great guide for on Machine Learning Mastery. Gentle Introduction to Statistical Power and Power Analysis in Python. And there is better coverage on methods to calculate statistical power linked above. A typical default value for the power, so in case you don't know what your power is automatically, a default value that a lot of people pick is 0.8. We can also create something called a power curve, which can help us see diminishing returns in our power as we iterate through sample sizes. So for example, if I was to use this code over here, I would get this power curve, and I would see that probably around 250,000 samples is where we start to see diminishing returns in our data. Diminishing returns in our sample sizes, and where collecting more samples might not be worth the extra power that we're receiving. So this is a power curve, basically. I guess there is diminishing returns after 210. That's correct. Another way to calculate which samples, so usually you'll be using this to try and calculate your sample size because you want to know how many samples can we collect how many samples do we need to collect in order to determine if if the correlation that we see over here is significant in some way, or do we have enough samples to, you already have your samples, and you need to say, okay, do we have enough samples in order to actually determine that? And that's actually what this A/B testing Kaggle workbook I shared at the beginning of this lesson is quite good at doing. The creator of it actually shows you how to determine if you have enough samples to actually go about what you're doing, to actually determine if what you have created is significant in any way. And there's a rule of thumb, which is basically 16 times sigma divided by delta squared. And then sigma stands for the current effect, and and delta stands for the effect size. So the current effect would be something along the lines of like, okay, you have a web page that has a 12% conversion rate, and you have and if you want to implement the new web page, then it needs to be at least 0.35% better. That's your effect size. What's the effect we're looking at to actually care? And in this case, we would have 0.12 as the sigma over our delta of 0.0035. That is what we're doing. And that is chapter 3. As you can see, chapter 3 was a bit of a doozy. Honestly, I really feel like this one is like you have to read it yourself in order to understand what's going on. So I was gonna have this video out over the weekend, and then like as I worked on it more and more, like I just kept adding more and more content to the notes until eventually I was like, this could go on forever almost. I'll probably keep adding a little bit more content to the notes, but the video I'm gonna have to cut it short because the video can only be so long, honestly. And yeah, that's chapter 3. Again, if you're at all interested in what we're doing over here, please make sure to like, comment, and subscribe on this video. Commenting is great for the YouTube algorithm, as is liking. Subscriptions are just, great to show that my channel is growing and getting the attention that I hope I have earned from you guys. And if you really like what we're doing over here, then YouTube memberships and Patreons are a great way to support the work and get a hold of the notes that we created over here. But as always, I like to do a little scroll through of the notes just to make sure that no knowledge is being withheld from anyone, and people are the knowledge is accessible to everyone. But still gotta value the work. It's something, right? All right. And we've actually been getting a lot of patrons recently, so I'm very excited at what we've done so far, and thank you guys so much for all the support you're showing. So it's basically 4,000 words worth of notes, of which I'll be adding more too. So anyone that is on my Notion pages and has all my other notes, you'll see that I add stuff to it occasionally as I come across more information. And I'm kind of trying to create a library of different things that are different notes that I want to put together. A library of content that I can hope to share with people later. But thank you guys so much for joining me, and I hope you have a great day.